So let's utilize this for something called motion maps. Let's say I've got a block. The block starts off at rest, but a little bit later it's moving. So it's got a little bit of a velocity, and then a little bit later it's here. And let's assume that each of these blocks represents the same time period. So this is some delta t here, and this is the same delta t here. Same time period. If you like, we'll call that 1 second. So clearly I moved over a farther distance in the same time period. I must be going faster. So clearly I moved over a farther distance in the same time period. I must be going faster. So I'm going to make my velocity arrow bigger. And a little bit later on, I'm farther down. Again, my distance has increased in the same time period. This is delta t here, from here to here. And so I must be going even faster. And so what's happening here is my velocity is increasing. My velocity is getting bigger. And since I'm getting a larger and larger velocity, I can say that my acceleration is in the same direction as my velocity. So my acceleration here is to the right. Each of these is a velocity. And so my acceleration is to the right. If I drew another motion map that looks something like this one, what you'll notice in this motion map is that the distance between my time positions, again, these are all the same delta t, okay, the same delta t each time, I'm clearly getting closer and closer together. My velocity must be getting smaller. And so my change in velocity is decreasing. Now what that means then is that my velocity, which is to the right, is getting smaller, so the change in velocity must be to the left. And so acceleration in this example is in that direction. Finally, if I have a separation where the distance between the blocks is the same, then each velocity must be the same. But if each velocity is the same, there's no change in velocity. These are all velocity. If there's no change in velocity, then there's no acceleration. And so the acceleration in this example is 0. So looking at part 1, if the acceleration and the velocity, very important now, if the acceleration and the velocity are in the same direction, the object is increasing in speed. If the acceleration and velocity are in the opposite direction, the object is getting slower, decreasing in speed. And if there's no acceleration, the speed remains the same, the velocity remains the same. Okay, there's a special case of one-dimensional motion where the velocity is constant. I want you to remember, though, these equations are only valid when the velocity is constant. And the equation really is nothing new. Here, if the velocity is constant, then the velocity is equal to some initial velocity. It never changes. It's always the same. And the second equation really is nothing you haven't seen before. This is basically distance equals rate times time. We've seen this many, many times. Rate is the rate at which your position is changing. That's probably not something that anybody ever said to you. But when I say distance equals rate times time, rate is velocity. It's the rate at which your position changes with respect to time. That's what a velocity is. And multiply that by time. This term simply is, where did I start? We always assume when you did distance equals rate times time in the past that you started at the origin. This is where you start, but that's not always going to be the case here. For example, I might say that the ground point is my origin, but I'm going to drop a ball from the top of the building. Then the top of the building is not the origin. I have some initial position because the origin is at the ground. So there's a difference there between where your origin is. Now generally you get to make that determination, but sometimes the problem will dictate a better choice for origin. We'll get to those later on. So this second equation really is distance equals rate times time plus where did you start. Constant acceleration gives us a different set of equations. If the acceleration is constant, that means the velocity is changing, and it's changing by the same amount. Again, this is not always true. We'll work with constant acceleration equations many, many times in this class. But I warn you that it's not always the case, and we will work with situations where the acceleration is not constant. A very good example of that is air resistance. When you drop something through the air, the velocity of the object being dropped through the air is changing. acceleration is not a constant. So here's one equation. The velocity equals whatever your starting velocity was, plus whatever the acceleration is times time. If we take a look at dimensions here, we have velocity, that's length per unit time, equals initial velocity, which is still the length per unit time, plus acceleration, which is length per unit time squared, times time. And so you can see that the time squared cancels with that time, and you get length per unit time equals length per unit time plus length per unit time. Again, this is dimensional analysis. I cannot add two things of different dimension, but I'm not. They're both length per unit time. Even if one's in meters per second and the other one's in miles per hour, I can add those together legally. It's not easy, it's awkward, but it can be done. A second equation of note is this one. And what this says is that my position equals my starting position plus my starting velocity. Remember, velocity is changing, so this is the starting velocity times time, plus 1/2 my acceleration, whatever that acceleration might be, times the time squared. Again, if I look at dimensional analysis, position is length, velocity is length per unit time, but then I multiply that by time, so the times cancel. And this term here is just length. Here I have length per time squared, but I'm multiplying it by time squared. And so when I put all that together, I just get length. So everything in this equation, each of these individual terms, has a dimension of length. Keep in mind when I say term, V0 naught t is a single term. 1/2 at squared is a single term. Terms are separated by addition or subtraction. Some other equations you'll see, and again, these are only when the acceleration is constant. If I don't have a constant acceleration, these equations are not valid. And this basically is position equals initial position plus my initial velocity plus a later velocity. This is the velocity at this time t. So at a later time t, this is the velocity I have. This is the velocity at time 0. This is the position at time 0. That's what I mean by V naught, or V sub 0, x sub 0. Those are positions and velocities at time t is equal to 0. So position equals initial position plus, take the initial velocity plus the velocity at the later time, divide those by 2, multiply that by t. And if I do some substitutions, basically, if I take this equation right here and I solve it for t, so v minus v naught over a equals t, and then I substitute that in here and here, and I work out the algebra, I get this equation. So you'll notice this equation has no time. So this is a very useful equation if I'm not working with any time as a given value. So these are some of your constant acceleration equations, and again, they're only valid when the acceleration is constant. If the acceleration is not constant, you cannot use them. A very good example of acceleration being constant is free fall. Okay, the acceleration due to gravity near the surface of the Earth is negative, and then I say negative because I'm assuming up is positive. So negative 9.8 meters per second per second. Near sea level, this might be 9.81. I live at 5,000 feet, so it's closer to 9.80, whichever you want to use. In fact, in a lot of cases, I'll just round it off and call it 10 meters per second squared. And that's just a round off value, so I don't have to think about my calculations too much. Generally, in any problems in the book, you'll use negative 9.8. In the English system, minus 32.2 feet per second, or minus 32.2 feet per second squared is the acceleration due to gravity. Again, that's near the surface of the Earth and at sea level. So let's look at a motion map for a ball that I'm dropping. Let's say I have a ball right here. Now if I'm dropping the ball, that means the initial velocity is 0. My velocity is equal to 0. Let's designate the position here at 0. Okay, now 1 second later, it's going to have fallen. And it's going to have fallen to about here. Now let's assume the acceleration is 10 meters per second squared down. And let's further assume that down is positive in this case. Normally I'll make down negative, but just to make life simple here for a minute, let's just make down positive. So what's my velocity? Well, let's go to the constant acceleration equations. And if I look at this equation, v equals v naught plus at. So a is 10 meters per second squared, and t is 1 second. My initial velocity is 0 because I dropped it, so that's 0. So 10 meters per second squared times 1 second, that's 10 meters per second. I'm going to say my velocity equals 10 meters per second. Question is, how far did I fall? Well, I can think about this in a couple of different ways. Since I have a final velocity of 10 meters per second and an initial velocity of 0, I can go back to this equation. So my initial position was 0. I started off with 0 velocity, but now I've got a velocity of 10 meters per second. So there's v naught and v. Divide that by 2, and 1 second has gone by. So that's 5 meters per second times 1 second. So 1 second has gone by. So I've moved 5 meters. So my position now is 5 meters. A little bit later on, I'll have fallen to here. 1 second has gone by. My acceleration says I go at a rate of 10 meters per second. So 1 second's gone by, I must be moving 10 meters per second faster. So my velocity must be 20 meters per second. 10 meters per second faster than it was 1 second before. I could use this equation again. I started off at 10 meters per second. Now I'm at 20 meters per second. That's 30 meters per second. Divide that by 2, that's 15 meters per second. I've traveled for 1 second, so I've traveled 15 meters. But I started at 5 meters here. So I've traveled 15 more meters, so I must be at x equal to 20 meters. So there's 15 meters in here, 5 meters in here. 1 more second later, I'm down to here. My acceleration is 10 meters per second, so I must have a velocity now of 30 meters per second. I started at 1 second time interval. I started at 20 meters per second. Then I went to 30 meters per second. That's 50 meters per second, but divide that by 2, so that's 25 meters per second. How long has it been? It's been 1 second. So this gap must be 25 meters, which means my new position is 45 meters. One last time, I get to here. My velocity is now 40 meters per second. I started at 30 meters per second. Now I'm at 40 meters per second. Add those together, I get 70 meters per second. Divide by 2, I get 35 meters per second. There's 1 second from here to there. 35 meters per second times 1 second is 35 meters. So I've fallen 35 meters in here. I must be at a position of 80 meters. But if I use the equation x equals x naught plus v naught t plus 1/2 at squared, I started at rest, so that's 0. I'm going to say that my origin is where I started, that's 0. And let me not use x, let me use y is equal to 1/2 10 meters per second squared times t squared. So at t is equal to 1 second, this is 1/2 10 meters per second squared, 1 second squared, and that's going to equal 5 meters. Second squared here, second squared is going to cancel. At t is equal to 3 seconds, I get 1/2 10 meters per second squared times 3 seconds squared. That's 1/2 10 meters per second squared, 9 seconds squared. That's 45 meters, which is exactly what I got at this time right here, 3 seconds. So you can see that that works out just fine for finding my position and my velocity. Okay, let's take a look at another problem here. Okay, you're driving an automobile at 115 kilometers per hour. You come around a corner, so now you're going straight. You notice a car 450 meters in front of you. That car has a constant speed of 75 kilometers per hour. How long will it take before you pass the car in front of you? Okay, the origin is your position when you notice the car. So let's put the origin right here. We have a number line. You're at x equal to 0, and here's a car up here at x equals 450 meters. You have a velocity of 115 kilometers per hour. The car in front of you has a velocity, call that v2, this is v1, of 75 kilometers per hour. Now don't confuse the v2 and the v1 with time 2 and time 1. It's vehicle 2 and vehicle 1. So the question then is, where are you when you pass the car and where is the other car? Okay, well immediately I'm not too crazy about my units, so let's change 115 kilometers per hour to 115,000 meters per 3,600 seconds, because that's 115 kilometers is 115,000 meters, and 1 hour is 3,600 seconds. So that's 31.94 repeating meters per second. And doing the same thing for V2, this is 20.83 repeating meters per second. Okay, so I can define my position, x1, equal to, and I started at the origin, so 0 plus 31.94 meters per second times t. And the other car, I'll call that x2, that's equal to 450 meters plus 20.83 meters per second times t. Now the question is, how long will it take before I pass the car? And I have to think about, what does that mean, to pass the car? Pass the car means my position is the same as the position of the car in front of me. So when, that's time, did I have the same position as the car in front of me? So the same position, I set them equal to each other. So I say that 31.94 meters per second t equals 450 meters plus 20.83 meters per second t. And in order to solve this, I got to bring all the t terms to the other side, so minus 20.83 meters per second t, subtract that from both sides, minus 20.83 meters per second t, and the left-hand side of my equal sign becomes 11.11 meters per second t. And the right-hand side is 450 meters. Now to solve for t, I'm going to divide both sides by 11.11 meters per second. And my left-hand side, I've just got t, and 450 divided by 11.11 is 40.5, and then I have meters divided by meters per second, but that's the same as meters times seconds per meter. The meters cancel and I'm left with seconds. So 40.5 seconds, which it should be. I'm talking about a time. So that should be a time. Then the question is, where does that happen? So my position is 31.94 meters per second times 40.5 seconds, and that's at 1,294 meters. Where is the other car? So that's x1. Well, x2 is 450 meters plus 20.83 meters per second times 40.5 seconds. So this is 450 meters plus 844 meters, and that equals, lo and behold, 1294 meters, which it should. If I'm passing him, we have the same position. So the position of myself and the position of the car in front of me are the same. So I want to graph those functions. I started, let's see, here's t is equal to 0, here's x. I started here at 0, and I am traveling with a velocity of 31.94 times t as far as position goes. So here's x1 equals 31.94 t. That's a straight line with a slope of 31.94, specifically 31.94 meters per second. That's the slope of that line. The other car started here at 450. He's got a slope of 20.83. It's not as steep as mine. His slope is about there. This is where we meet. That's 40.5 seconds. And here's the position, clearly not to scale, 1294 meters. So this is the line x2 equals 450 meters. That's right here. Again, not to scale. Plus 20.83 meters per second t. Notice they're both straight lines. They're both constant velocities, hence the lines are straight. And the intersection of the lines is where the two cars meet. And the t-intercept, the t-coordinate of that point, is the time where we both meet. So this point is 40.5 seconds, 1294 meters.